Right. Okay, so I'm starting the recording now. So I hope everybody will manage to also somehow look at the recording. I don't know. I think the link was probably not working, the links that I sent, because I thought it was somehow linked to my account, so probably that didn't work via the link that I sent. But if you go in the chat, because we're using the same chat for all the meetings, you should be able to actually get access to all the recordings via the chat. So you can do that. And then Chuck, I don't know if you know a way to like save the recording on your computer and then share it to somebody else, or
what you have to do is download it. When it comes up in the chat window, it says okay, recording finished or something, and then you click on that and go to some Microsoft cloud site.
Okay, because again, like open in stream, get link, learn more. So I don't have really an option of like saving it. I'll see once I open it in stream, maybe I can then save it.
You can download it and then give it to Sam.
Okay.
That's what I did last time. I don't know if
Okay, so I try to do this for all the recordings, and then we can share them either on the box or folder or via the Victor website, so then everybody can have access to the recording if you cannot attend the class. Let me quickly share my screen to show you some updates on the schedule. All right, so this is the latest schedule. There was some changes due to some availability.
Can you blow it up a little bit?
Yeah.
I can't see it. Sorry.
You see it now?
Yeah.
Okay. All right. So yeah, there was a few changes there and a few additions. So we're going to still start with Chuck today. That's going to talk about ordinary differential equations, and then we're going to move to some various volcanic processes there until spring break. And so we just shifted the magma degassing to allow the code developer of the Sulfur X code, Shuo Ding, that should be able to actually do a presentation on Sulfur X on March 6th. And that's the day we're going to talk about magma degassing, so that's really great to have that. And then after spring break, I just got confirmation from Mark Giosso and Wendy Boson that they both are willing and able to talk about their codes. So that's really great.
Oh, cool.
So yeah, so Mark is going to talk about MELS and the Enki portal. It's pretty similar to Victor. I actually went through it yesterday, and it's actually on Jupyter Hub, and it's got a lot of resources and Jupyter notebooks for magma differentiation and crystallization and mixing. It's got all the versions of MELS in there, so he's going to talk about that and do a few demo. And probably he actually encouraged us to actually get an account on the Enki portal as well, so then we can follow what he's doing on that day. So I'm gonna send you an email about that a few weeks before, so then everybody can get an account and follow that presentation. So it's gonna be on the 27th of March. And then for the moment I put April 3rd, but I'm still waiting for confirmation from Wendy in exact which day she's going to talk about the magma chamber simulator for magma storage. That's also super cool. And so that's going to be in one of these Wednesday in April. So I'm going to share that with you. I think there's not going to be too much changes from now, but I'm going to share that on either on the chat or via email, so then you can get this updated version of the schedule with you. All right. So second thing I wanted to do before starting with Chuck is asking everybody, whether you guys have any questions for those who managed to, for example, get a Victor account, or even those that didn't manage to get a Victor account. But if you have any question about what we talked about last week, which was presentation of Victor and the hub, and just a few basic info about how to create a Jupyter notebook. So do you have any questions? Please don't hesitate to do it now, because then we can really, like, know what the major gap are, and we can fix that. Yes, Sarah?
Yeah, I just wondered if you could explain again about the different server options and how you go about choosing which size you might need.
Yeah. So I think the basic idea is that for any basic work that require just either to run a Jupyter notebook, or to create one, or to use the desktop, or any application in the launcher pad, you will select the small server that should have enough resources to actually run most of the codes that are on Victor. Now, if you want to start doing some, for example, for probabilistic modeling, where you want to, start investigating uncertainties with your model, and having some batch of runs that require more memory and more CPUs, then you can choose the bigger server, so either the medium or the large one. Just note that for the moment, we haven't really implemented any workflow that is dealing with that. We're actually in the process of doing it. And so for the moment, we don't have any code that we can run probabilistically, but that's actually gonna be one.
We're gonna run our code probabilistically in about 2 minutes.
Yeah, exactly. And we're actually planning on putting some tools, like, for example, for Titan 2D, putting the what is it called, the probabilistic, how does it call exactly, the one with that Arbani is using on that is already on VHub, that is
right.
already all set
I'm
up.
blanking too.
Yeah, I don't remember exactly the name, but basically, yeah, that's the goal. So if you do need to use a large server for a long period of time, probably the best is to actually email us and email Sam and request that in advance and see if that's possible or not. But otherwise, yeah, for all other normal tasks, I would just use the small server. I don't know if Chuck, you want to add anything to that.
Yeah, I mean, it's just lighter to use the small server. So, and for most things, especially like today, you're not going to need anything else besides the small server. There's nothing wrong with choosing a bigger machine and checking it out, and you can use it if you want to. So far, we haven't run up into any issues, as far as I know, about use, or somebody using way too many resources or something like that. So I don't think it's any problem right now, honestly, to choose whatever you want. But as Sylvain said, choose the small server if that's what you need, and scale up from there. No big deal either way, and it should be transparent in terms of, when you sign on, you're not on a different account or something like that. You see the same window and all that kind of stuff. You're just you just spun up an instance of it's called an instance, and all these servers are running on Amazon Web Services, and so you're basically spinning up an instance of that computer. Doesn't necessarily even reside on a single machine in space somewhere. It's just how many resources are available to you, essentially. It's my understanding anyway. Cool. Okay, yeah, so go ahead, Sarah. Use a medium machine or whatever, or heavy machine. Just, it's probably not going to make any difference right now unless you're doing something, wild.
I got it on the recording.
Yeah. That's fine. That's fine. We'll let you know if suddenly we ran out of money. We're gonna let you know. But I think we're okay. It does cost money to run these things, but
yeah,
you know,
I actually just check, and yeah, the small server's got only 8 GB of RAM. So for example, you know, if you know you're running a code that need more than that, it's probably good to go for a bigger server. I know there's some codes that that use a lot of RAM. If you know already that your code is going to use more than 8 GB of RAM, then you may want to go for a bigger machine. Yeah.
Thank you.
yeah, but you know, freely explore it.
Yep. All right, we got a question from Antonio.
Oh, yes. Well, it's not sadly a question. It's more a request on the course, because I saw within the server there's quite a repository of DMs and cartography, like a server core cartography. I have a request if by the end of the course we could make a little lesson on that, to go on through that library.
Yes.
Sure.
Yes, that's
Yeah.
a great idea. Everybody eventually needs a DEM, if only to plot your sample locations on or something. So yeah, we can talk about that. And I don't know when it can fit in, Sylvain, but probably if it can't quite fit in, then we can meet at a different time too.
I think we can fit it in April. We can do that in case we manage, you know, to go through the schedule, and we can definitely talk about that. I think we can do something about DEMs and like raster processing. We can show you some of the tools we have to process rasters and like change coordinates of DEMs or you know, clip a DEM or things like that. There's a couple of tools on the hub that can do that, so we can definitely have a session on that later on. Yeah.
In the meantime, you know, if you're familiar with QGIS, for example, that's on Victor. If you start a console window, you can spin up QGIS, no problem. And a lot of tools are available for manipulating map data, like GDAL is on Victor. PyProj, which is a map projection program, is on Victor, and GMT.
Raster.io as well is in there.
Yeah. So yeah, we'll do something with that, and let's explore around. Feel free to explore around as well. I'm sure I know there's a bunch of people on the call who are much better at DEM manipulation than I am, so feel free to explore, Glenn and Felix.
Yeah.
Okay, anyway, yeah.
Anybody else have a question about the hub? Okay, so I think we're gonna do that again next week when we start each meeting. I think we're gonna ask you if you guys have any questions, since probably some of you didn't manage to get a VIAB account or a Victor account yet. So I'll keep saying VIAB, Victor account yet. So we're gonna do that next week again. And also, don't hesitate to use a chat to ask a question. Don't hesitate to use emails to ask questions to us. It's really, you know, we really want to get your input on that, and it's really important that you give us as much feedback as possible, so then we can improve the hub and make it better for the community.
And remember, we decided not to create a Slack channel for this class, but if people would prefer to communicate by Slack, that would be great. Sure. It just happens last year nobody used it, so it was kind of a, you know, I got tired of monitoring it and nobody was using it. But if people want to use Slack, it's fine. You know, we can boot that up too.
Yep.
However you guys want to do it. But email works pretty well, honestly. Or talking here works well.
Yeah. All right, cool.
You want me to go ahead?
Sure. Yeah. Thanks, Chuck.
Sure. So today I was going to talk about ordinary differential equations in volcanology, and it's not that I'm trying to go off the deep end or something like that, but I just think it's a nice gateway to understanding some aspects of coding, and especially how you can, coding can actually simplify your life for actually, being able to solve problems that you come across in papers or in your research. And normally, if you're like me, you go, oh, there's a differential equation, and you skip over it and read the rest of the paper. But, to the authors, often those equations are super important to their story. And we want to become versed in just, comfortable with those types of equations and understanding them. Super important in volcanology, of course, because they deal with things like rates of change, which is something we all care about. And so I'm going to go through a few examples of that kind of thing today. One problem we're going to look at is called the tank problem, or you can think of it as a magma reservoir problem. So we'll look at the, how you use the differential equation to understand the change in chemistry of a magma chamber with time, using very simple models if you're a geochemist, but it might be a gateway drug for you to think about using differential equations in your geochemical modeling and that sort of thing. If I have time to get to it, we'll talk about using solving differential equations related to ballistic transport and how codes are simplified. In Python, for example, I'll just present you with one of those and so on. So maybe I can share the screen, and if you are on Victor, great. If you have an account, it'd probably be good to go to it, so you can follow along with at least the initial steps of today. And we're recording it in case you're unable to do that right now, but we'll get there. And I guess when Sam shows up, we'll we'll stop for a second and answer questions about Victor. So, and getting an account. So a nice thing about Victor is I just went to the web page today, signed back in, and got right back to where I was last week. So you can see Untitled 8. I'm terrible here at saving my notebooks, apparently. So don't follow my example, but on Victor, it's nice. It just booted me right back into where I was, and my notebook was still up and saved and all that kind of stuff, even though I didn't bother to do it. So anyway, so remember last time we were talking about using Victor as a kind of a scientific notebook in addition to being a computational platform and tool. And so I just want to emphasize that this is a key thing about using Jupyter notebooks, is they provide a record for you of what your research is all about and what's going on with it. And increasingly, I'm addicted to it. I use this all the time now to sort of record calculations I do and things like that. I still keep a written scientific notebook I take notes in and stuff like that. But man, this Jupyter notebook idea is very powerful because it's integrating the code and the text in a way that I just haven't been able to do before. And for me, that's quite powerful. And I'm kind of at the end of my career. I've been doing this for 40 years, and I still have notebooks I worked on in the, scientific notebooks written down in the 90s that I go back to. I'm like, what is going on with that? What was I thinking? I seem to have been a lot smarter in the 90s than I am now. But anyway, it's just going to make you very powerful as a scientist if you manage to keep up with these notebooks. And I'm just pointing out that Jupyter and Victor super nice way to approach that. So just to review for a second, remember if I double click on that cell, which I just did, I see how to enter text in the cell. And so I can use headers of different sizes using the hashtag or £. I use latex notation to enter equations and to define variables and that sort of thing. And when I go up to this arrow or whatever you call it, sideways triangle, I can run that cell and that cell becomes formatted. Okay, so this cell is an example of a markdown cell, and I can have markdown or code cells. Forget about raw, but markdown and code is pretty useful. So this is a markdown cell, and I use it for writing text, writing down equations, and that sort of thing. And then here's our little code from last time, just implementing that equation in Python, where I just did this variable assignment and printed out the lithostatic pressure. And so when I run that cell, which is labeled code here, it executes it. And sometimes we get confused, like if I make this a markdown cell by mistake and I try to run it, then you know, whatever happens, it's like, that's not what I expected. And so you just want to check that switch up here at the top. If I run this as code, it'll probably throw me some error message because it doesn't understand Python, right? Or that's not, it's looking for Python and it doesn't understand my my markdown. So that kind of thing does come up on the notebook, and I just wanted to point that out. And there are a few other things about notebooks which we'll come across as we move on. So anyway, today I just wanted to expand on this notebook a little bit, and I'm going to continue down, and I'm going to start by making another markdown just so I organized my problem a little bit. And I wanted to ask you guys if you're familiar with this idea of laminar flow in a conduit. And you know, a lot of what this class is about is what's happening to magma in the subsurface, what happens, how does it get to the surface, and then you know, what does it do when it reaches the surface. And if we think about it, you know, one of the earliest sorts of ways to model volcanic systems is by looking at laminar flow in a conduit. And we don't have time today to go through and derive this equation, but it sort of gets us into using these ordinary differential equations. This one doesn't require it. It's still an analytical solution, so I'll take advantage of that. But let's say what we want to know about is flux, and I'll define that as with a capital Q here in my markdown window. And that's going to be equal to it's going to depend on several variables, which I can simplify as a laminar flow problem. In laminar flow, I've got a vertical conduit. I'm going to make the vertical conduit circular. So there's a simple analytical expression that depends on the radius of the conduit, the viscosity of the fluid, in this case magma, and the pressure gradient driving flow. So let's just look at that for a second. It's going to, by convention, it's going to depend on, it's going to be negative, which I'll explain in a second. And then it depends on a fractional relationship. So I can write that in LaTeX with this frac command. And I can say pi r to the fourth, which comes out of the integral for the equation in laminar flow conditions, divided by 8 mu, where mu is the viscosity. And then it depends on another fraction, which is the pressure gradient. So dp for pressure dx. Okay, and so if I run that in my notebook, I go up again to that triangle, or I can use a shortcut, which is shift enter. It gives me this equation for laminar flow in a conduit. Oh. And the other way to describe that equation is, let's see, it's Poiseuille flow, right? Poiseuille flow. How do I say that, Sylvain?
Bernoulli? That's what you want? Or you want the Bernoulli? Yeah?
No.
No, the other one, the Poiseuille.
Thank you, Poiseuille.
You said it so badly, I couldn't even tell if it was Bernoulli or Poiseuille.
I'd say it's laminar flow. Good thing I don't depend on French for a living. I only depend on French scientists. Okay, so that's my flux, and then a common approximation for this. A guy named Claude Japar sort of used these equations in a huge number of papers in the past. Andy Woods, is another person who used these equations. I can approximate dp dx as equal to minus and then the fraction of just the density difference under buoyant flow conditions. So I'll just say rho r for the density of the crust or the density of the rock minus rho m for magma. And let's just put that here. And depends on gravity, and it depends on the length of the conduit. So that's just like my rho gh from last time, divided by d length, or dl in this case. So I can write that approximation, and then I can say Q as a result is going to be, if I just do that substitution, should have done it before, is going to be this expression times this expression, rho g, right? Let's see, just get this out of here. Like that, and close. I don't need that fraction anymore, I don't think. And I don't need that minus sign, that goes away too. So I think I can get something like that. That's about right. Yeah, okay, so now I've just developed this analytical solution to flow in the conduit around variables that as a volcanologist or as a geologist I might be able to understand a little bit. So R then is the radius of the conduit, mu is the viscosity. I've got these terms for the densities of different things and gravity. And so I'm not going to write them all out here, but you get the idea that in your notebook you would then define these variables, density of the crust, and probably give the units. You can check the dimensionalities of these equations and stuff like that. Whoops, messed that up. So I got to put a backslash there for the row. And you can go through and develop these things. Okay, so here's an analytical expression we can solve. That is, by analytical, in this case, I just simply mean that if we write this expression, the flux is equal to the terms on the right-hand side. I can fill in values for those and actually calculate the flux, right? So let me just do that in code so we're all on the same page. And at the same time, I want to develop a couple sort of bits of notation and tools and approaches that we're going to use today, okay, to look at other codes. So let's just say I'm going to define, now in math, I always, of course, try to use single letters or Greek letters to represent variables, sometimes with a subscript, as I did here for these different densities, rho and magma. And in code, I want to actually use more of a plain language to make my code readable. So instead of saying gravity is G, I'm just going to say gravity is equal to 10 meters per second squared, right? And that meters per second squared is the unit, and I want to include it, but it's not really part of the code. It's just notation for me. So I'm going to add that hashtag there, that pound symbol for the units. Okay, and so then I'm going to assign a couple other variables. Let's say the conduit radius. Don't hesitate to write these things out. You can always put underscore in your variable name. Conduit radius, we'll just, you know, make something up, 10 meters, right? It's my radius. Viscosity is, whoops, got to spell it right. Otherwise it's not readable. Viscosity. Oh, what are we going to do? Sort of, I don't know, 1/6. And that'll be in a Pascal second. So that's a very relatively viscous magma. And then I'll just do density of the crust is equal to 2670 kilograms per cubic meter. And the density of magma is 2400 kilograms per cubic meter. Right? So that's easy enough. And then I could, just like I did last time, implement this equation directly in this cell and solve the problem for Q. So what I want to know is the volume flux. So that's my variable. But I'm going to do something a little bit different now, because this, you know, just writing these analytical expressions in the code is not that useful. So I'm going to define a function which implements this particular equation. And so to define a function in Python, if you've never done it before, use this key phrase DEF for define the function. Other languages like C, you would write out function or whatever. In different languages, it's different meaning. But DEF in Python is shorthand for I'm gonna call this a function. So I'm going to define a function called laminar flow. Could be a laminar flow in a conduit. I don't want to type that much. Okay, and I'm going to pass the function variables. I'm going to come back that to a minute, and I'm going to put a colon there. And the colon means everything that follows is going to be part of that function. And you can see what the Jupyter Notebook does for you as an editor is it indents. It assumes you're going to want to indent here. And in Python, that indentation is important. It means this following text is part of the function. So I'm going to give it a comment here, laminar flow in the conduit. And I'm going to then write that expression. And I'm just going to say Q, I'm going to use a little shorthand here. I'm going to say Q is equal to np.pi times r raised to the 4th power divided by, and then open parentheses, because in my order of operations, I want to make sure everything's copacetic in the denominator. So I'll just say mu. I'm just going to use these math variables here, and I'll explain why I'm doing that in a second. And then that's going to be times the difference in density. I'll just say rho r minus rho m, and then times gravity, if I wrote my expression right. And then what the function does is it returns a value. So in this case, I'm going to return Q. Now you can see that when I just simply implemented the latex I wrote up here in the markdown in the function down here. And that's a nice thing about Jupyter Notebooks, again, is I can sort of see that parallelism as I go along. I definitely can't remember the equation for laminar flow, despite having worked on it for many, many decades. But I can keep track of it easily in the notebook. Okay, so I have to pass variables to this. And so what I'm going to pass is, sorry, somebody's asking a question.
Can you remind me what NP, why do you put NP first before the pi?
Yeah, I'm going to get there, but I can do that now. So remember NP, I think I used it up here. Oh, I guess I didn't use it. Okay, so NP is a set of libraries that allow me to do quite a bit of math and matrix manipulation and some other statistics and that sort of thing. So it's a library of mathematical tools statistical tools, and so on that exist in Python. So the community essentially has developed this library. And it's called NumPy. So at the beginning of my code, I have to say import NumPy as NP. Why is it called NumPy? I really don't know. I guess it's numbers in Py, something like that. Numbers in Python. But that's a library I need to import. And so when I use this form, which has been sort of adopted by the entire community, I don't have to type NumPy to call a NumPy function. I just have to type NP. So down here, I say np.py to refer to the value of pi. So I'll come back to that more in a minute, but that's the short answer, Sylvain. And then thanks for the question. So then I have to pass some information to this code. So let's just do it in order. I have to pass it R for the radius, mu for the viscosity. I have to pass it rho R. I have to pass it rho sub m for the magma density, and G. And probably I want to define these variables inside this function. So when I come back to it and reuse it, conduit radius and so on, right? And I might even want to say the units here and so on. So the more information you give yourself in this sort of documentation, the better off you are, and the more usable your code's going to be. That kind of thing. So I can write whatever I want back there to give myself the documentation I need. And okay, so if I let me just get rid of this line here for a second. So I can now run the code in my notebook, and so let me just do that, see what I get. Oh, nothing comes back at all. Well, that makes sense. They didn't ask it to do anything yet, but when I ran it, I could see if, at least in terms of gross syntax and that sort of thing, if my code is okay, and it is, because I didn't get an error message. If I, dropped parentheses or something here, it would give me an error message, and I would have to track that down. And so that usually happens to me when I type in code the way I just did. I'm surprised it didn't this time, but there you go. Okay, so then I would use this expression. I would use this function. And so what I'll do is I'll say, well, I want to know the volume flux. That's what I'm going for here. And instead of writing out the mathematical expression as I did before, I'm going to say laminar flow. That's the name of the function I defined up here. And then I have to pass laminar flow these variables. Often when you're passing variables back and forth and related information, those are called arguments. So sometimes you'll hear me say, I'm passing an argument or whatever. Okay, so let's type it in. The important thing is I'll type the variables in the same order they're going to be used by that function. So I'm going to say conduit radius is next, and then viscosity, I can type correctly, and then I'm going to put in density crust, and then I'm going to put in the density of the rock, of the magma density, magma, and I'm going to put in gravity. Okay, so the key thing here is, let me try running this now. I put a little indent here by mistake. I got to get rid of that, otherwise it'll bark at me. And I'm going to run that. Still no information, which is good, but so what I did is I called this expression. What comes back from this expression? I say return Q. So volume flux is going to be equal to Q in this case. And so what I can do is now say print volume flux And I think that's in cubic meters per second, right? So I'll just put that out there like that and run that bit of code. And so I get the volume flux from this conduit using this expression in cubic meters per second. So I know for some of you, you're Python wizards and you're just bored in this part of the presentation, but I just wanted to get people on the same page about these functions because they're about to appear in these examples of ordinary differential equations. So that's sort of how we go, how we roll in defining functions, and over time, your notebook becomes filled with these functions, and you want to reuse them as you get more and more proficient and as you solve more and more interesting scientific questions. You're going to be reusing these functions as you go along. And so a key element here is this indentation. So you can see everything under here is indented. That means it's part of the function. So Python relies on indentation to define spaces like functions and other activities in the code we'll get to, like loops and that sort of thing. It's all using this indentation. If you're used to a different language like C or Perl, you find that really irritating, but you know, it's how Python does it. You get used to it. And it's got this colon at the end of the expression. And notice that I don't need to use the same variable names inside the function as I use in the main part of my code. The main part of the code, I'm really spelling out these things and I'm giving myself a clue what those variables are all about. I'm using sort of plain language to describe the problem. When I get into the function, I just reverted here. That's what I do. I reverted to that sort of mathematical notation, which I developed up there in the LaTeX. And that means I can bring in other, you know, I can call this with other variables I've defined in other codes, and I don't need to rewrite my function. So if you haven't got a lot of a coding experience yet, that may not make sense to you, but it becomes super useful down the line when you start reusing bits of code. So I know there's some Python experts here. Anybody want to add anything to that before I go on?
Can you just talk about the space? I mean, where do you need a space and where it doesn't matter if you put a space or not?
So I can put in as many blank lines as I want, no problem. So I can run that. Doesn't matter how many blank lines I put in. I put it in to make it readable. You know, you can see I created a block of input variables here. And so, you know, I surrounded those by blank spaces. That's just how I do it. I might even give myself a note here, like here are the inputs. Thanks, Sylvain. That's a good question. And then for this indentation, I need to make sure that if it's part of the function definition, it's all indented. So all these things are indented, particularly the Q equals here has got to be indented and the return Q has got to be indented. And then everything down here is outside the function. And so I don't indent that. I don't know if that answered the question.
Yeah, and what about inside the equation you have for Q? You know.
Okay. Oh, okay. So inside the equation, again, blank space doesn't matter, but the order of operations really matters. And so inside the equation, let's look at the order of operations for a minute. The R ** 4, that's how Python does the superscript. So raising R to the 4th power times the asterisk is just the multiplication. So that's pi times R to the 4th. In the order of operations, R to the 4th happens first, then the multiplication. It doesn't really matter, but well, yeah, it does matter, but that's how it does it. You don't need to keep track of that when you're raising things to a power, but then this is the divided by. And you notice that mu times 8 is in the parentheses here, and so I've got to define the entire denominator here. So if I delete those, Let's see what happens. I'll run that again. Oh, I get a really strange number. You know, my flux is not going to be equal to that giant number because I've multiplied by the viscosity instead of divided by the viscosity in that case. So the order of operations is super important. The spaces between the asterisks or the minus signs, they don't matter. Okay, so, but you know, the parentheses matter a lot. And you have to make sure you know, just algebraically you're doing things in an appropriate order. So here the parentheses is saying do that difference and then multiply it by G, right? Obviously that's important. So yeah, but I can put spaces around wherever I want, and it just depends on you to you know, how you want to read the equation. It ignores the blank space in this equation. And then this NP pi, I passed over it. This will come up quite a lot, but NP is this shorthand notation for NumPy, which is this library of functions like the one we just wrote and related tools in Python. And when I say np.pi, I'm actually calling in NumPy the specific function called pi, and that is simply returning to me, instead of like returning Q here, it returns the value of pi, 3.14159, whatever. So that's super useful because then I don't have to define pi in my code or something like that. I can just use it, and that'll come up again and again. Okay, so there's that expression, and let's see. So if I'm actually doing using this scientifically, I just want to describe one more thing here. Let's go down. Let's change these inputs a little bit. I'm going to go down here. I'm going to just copy that code into the next cell. And so if I run it again down here, I get the same answer. And note that I don't need to repeat the function definition because I've already run my notebook, because I've already run this cell. My Jupyter notebook is now fully aware that that function exists. And I don't need to repeat NumPy either. So actually, if you look at notebooks on Victor, usually I can insert a cell. I want it to be above. Let's move it above. I can insert a cell. There it is, up here. And it's a coding cell. And I'll just put all my import statements in that one cell. And so if I run that cell, then I don't need to include that import statement anywhere else in my notebook. It's good and bad. Sometimes that messes you up, but I'll try to point out when that would mess you up. So anyway, I just repeated the code here a little bit. Now let's do something different. I mean, you know, a bunch of you are geochemists. We don't really know what the viscosity is, right? In fact, it's complicated. So there's variation in the value of the viscosity just based on the chemistry and the temperature of what the lava is. We can't know that. So there's random variation in the value of the viscosity. And so being able to say, well, I know the viscosity is 1e⁶, that's kind of, you know, simplifying your life a little too much, right? So maybe we can characterize the variation in viscosity as a random variable. So I've made these variable definitions here for viscosity, but let's just say, well, I'm really not confident in what the value of the viscosity is, even after I run my, you know, complete analysis through melts. I'm not really sure of the temperature. I'm not really sure of the, you know, the bubble fraction and, you know, whatever. There's all kinds of complicating factors, as you know. It's a fascinating thing in volcanology. So why would I use a constant value for the viscosity? I mean, I'm kind of fooling myself, right? Oh, I know the value of the flux to the 9th decimal place. Well, no, you don't. So let's just instead of assigning a value to viscosity, we'll treat it as a random variable and assign a range of values to viscosity. And there's a bunch of ways to do that, of course, but I am going to use NumPy again to assign a range of values to viscosity. So I'm going to use NP because, hey, I'm using a NumPy command. And then there's a set of functions in NumPy called random. And one of those is called normal for a normal distribution. And I'm going to pass normal distribution some arguments. The first argument is going to be the mean. Let's just say the mean is 1e to the 6th, like I wrote before, so 1,000,000. And then let's just say the standard deviation is 1e to the 5th. And I'm going to get 1,000 samples of that value. Okay, so if you Google NP random normal, you'll get more information than you ever wanted to know about this. But let's just use it right now. So now I am assigning viscosity to be a random variable. The mean is 1,000,000. The standard deviation is 100,000, and I'm going to get 1,000 samples. So let's just run this and see what happens. Okay. We want computers because we want to do things over and over again. So here's the random variation I get. That's 1,000 numbers. Boy, it gets boring to look at those numbers. But anyway, that's my random variation based on my uncertainty in the actual value of viscosity. Okay, so I don't really want to print those out. I printed them out to show you that I get a set of numbers. The set is bounded by a square bracket that represents an array in Python. So it actually created something called a NumPy array, which is called volume flux. So let's actually just make a histogram of this. And to make a histogram, I need to add some more functionality. So I'm going to import something else. I'm going to import matplotlib.pyplot. Well, that's a mouthful. I don't want to type that over and over again, so I'll call that PLT, which is what people normally do. And so I got to run that cell so the rest of the cells know about that library of functionality. And so when you look at some of the codes that, for example, Sam has put on Victor, you might see a laundry list of 10 or 20 of these import functions. And they're all like invoking more functionality to use in your code. Okay, so now I can actually plot the data. And so I'm going to say PLT. Remember, that's my shorthand for that plotting function. And I'm going to use a function called histogram. And I'm just going to pass it volume flux. Well, let's just leave it at that for the moment. So when I run that code, I get a graph. Okay, and so on the x-axis is my volume flux, and on the y-axis is count. So I'm going to make that a little fancier, just so I know I can remember what's going on here. I'm going to do plot x label is volume flux, and I'll probably say meters cubed per second. You can make that nicer looking with some additional, you can make the subscript and stuff like that in Python. I'm not gonna bother right now. You can get into making nice graphs. And then y label is just count. It's my frequency distribution. And then you can see it gave me a bunch of output here I don't really care about. If I use this plot show command, it'll get rid of that kind of output. So I run that. Oh, geez. I got to put that in quotes because I'm trying to write a label. I'll run that again, and then it gives me my histogram. And I can do things like control the number of bars and stuff like that. But you can see that I get kind of a normal distribution of volume flux, with a range of like 8 to 16 cubic meters per second, something like that. And it's got a kind of a normal distribution shape to it. And that makes sense, right? Because I'm taking a normal distribution as a random variable, and I'm putting it through a linear equation. So the output's going to be linear with respect to viscosity. So the output is going to be somewhat like a bell-shaped curve as well. Okay, so that's a lot. I know if you've never written Python before, you're like, huh, what did he just say? And then, so we're all at different levels and that sort of thing. But that's the key take-home message here is you can document the math easily using these markdown windows. You can define your variables easily in the notebook. You can import these functions, these libraries, which give you more functionality in your code. You can write your own functions like this, define laminar flow, do the variable assignment, print out values, and it's simple to explore stochastic variation in your model, in your view of reality, by introducing this kind of thing, right? This viscosity random variable. So that's
so
what
Chuck,
that's...
there's a question about what if you want to export this graph as a JPEG or PDF or anything else?
Good question. So I'm going to say plt.savefig. So that's another function that's part of matplotlib.pyplot, and I'm gonna save fig, and then I'm gonna give it a name. I'm just gonna close out that parentheses there. I'm gonna give it a name, and I'm gonna specifically say // and so on Victor and on most platforms, that // means save the figure in the directory I'm working in now. And I think this, I can't remember where I'm working now. Let's see if this works. I'm going to put down the name, my histogram, and I'm going to say .png because I want a PNG. And then I can specify even the DPI. So I'll say DPI equals 300. Maybe if it's for a journal article, you want 600 or something like that. And I probably want to spell histogram right because I'll never find it again. And I run that, and I don't think it's, did it save it? Let's see. My histogram, here it is. And so, well, it doesn't fit in my window, but I can then, you know, just grab that, download it to my computer or whatever I want to do, right? So it works.
So by default, it's going to save it in your user directory, right? In your
Well, that's why I used the // is to make sure it was going where I thought it would be. You know, you could even, like, if you had a directory structure where you were going to work in like my paper directory, if you had that on your computer,
yeah,
on Victor somewhere, a subdirectory, you could specify that as well. Boy, not spelling very well, but anyway, that's the idea there. Okay, so you know, matplotlib, I mean, I'm pretty much a basic user of matplotlib. It's got a huge amount of functionality, which you can explore for scatter plots, mapping, whatever you want to do. But anyway, that's the sort of...
We're going to raise hand from Antonio.
Hey, Antonio. Sorry, I'm not seeing that. I'm sharing my screen, and that's...
I can do it.
Yes, okay. Just a little question. If we want, for example, to export the table to an Excel file.
Yeah. So I would save that as, so we can use a different library, for example, called CSV for comma separated variable, and I could save that. I could save it as a comma separated variable file. There's a couple ways to do that. So yeah, I can.
You can also use NumPy if you have a
a
NumPy array. There's a .to-CSV function, and that will that's perfectly readable by Excel, so that would work. I also saw the question about exporting the graph to like multiple different types of file, like a PDF or an SVG. That you can actually just do that in the savefig if you change the extension. I think for some of them, like for the PDF, it doesn't take a DPI perhaps, but it automatically recognizes and will save it as it has basically all those commonly used ones. So yeah, JPEG, PNG, PDF, and SVG I think are all there. I'll check if there's anything else.
Here's the JPEG. So yeah, it'll do that, and so I think later on we're going to talk about manipulating data a lot more, maybe using something like pandas, or you know, we can use NumPy. Yeah.
Yeah, because multidimensional data is, you know, where everything is kind of creeping towards, I feel like, in volcanology and just in you know, data science reliant fields.
Yeah, and there, for example, there's a bunch of geochemists on the call today, and you know, you guys want to export tables of data, right? So we'll have to explore those tools in more detail. But there are definitely tools available. Check out CSV, check out export capability in NumPy, and then if you really want to go on, look at something called pandas, like the animal pandas, and we can go from there. All right. So yeah.
My recommendation is working with pandas. I make tables and I write CSV files in pandas because it's very easy to manage, and you can insert arrows or columns or whatever you need. So my recommendation is using pandas basically.
Yeah, I think that was Felix. I agree totally. It's pandas is pretty useful. It takes a while to get used to, but once you're used to it, it's extremely powerful for multivariate data like a geochemical analysis. So we'll have to get there. But I kind of wanted to go on to the ODEs, so let me do that, and I'll just go through these codes. We've been on for more than an hour, and I want to get to this. Maybe I'll go through some of this relatively quickly, with the idea being that these notebooks are on Victor, and you can take a look at it. So this notebook is called Solve ODEs. It's in that shared directory on Victor, and let me go through it a little bit. So this is by way of an introduction to sort of problem solving for you guys. Maybe you are an expert in solution to ordinary differential equations. Maybe you've avoided it like the plague in your career. I think in both cases, it's useful sort of looking at how these things fit in with Victor and Jupyter notebooks and that sort of thing. Okay, so I'm just going to go through this, just work through this notebook with you. If I open a notebook like this, one of the things I do often is I hit this double arrow. This double sideways arrow, and it means play all the cells, run all the cells in my code. So I'm just going to do that, and it goes down to the end here. In this case, it's a pretty short notebook, so it runs it pretty fast, and it just makes, if I get an error message at that point, I know there's something amiss in my notebook, or in the notebook you just downloaded. But usually, if somebody's giving you a notebook, hopefully they've checked it, and you can check that they've checked it by running that double arrow right up there. Okay, so I'm going to zoom in a little bit here. All right, so I want to talk about a couple of things. So here's like the I think the simplest ordinary differential equation, which many of you have encountered. Say dy dx is equal to k times y. So why is this an ordinary differential equation? It's because I've got a variable. Like maybe y is the fraction or the abundance of some radiogenic isotope, and dx is how that fraction varies with time, and that depends on the current fraction, right? So y is appearing here on the right hand side and on the left hand side of the equation. There might be a constant k to be the degree, the decay constant or whatever in an exponential model. So this is like a relatively simple differential equation. And the reason I'm showing it to you is if you specify initial conditions, like you say at time equals 0, for example, x equals 0, y equals 1, just for example, and then it can solve that expression, and it's got an analytical solution. Y is equal to e to the x, and so that's a famous relationship in science. Euler and others first started working on this, and they found the transcendental function e, the scaled integral under the curve. This is the curve of a hyperbola. They're like, oh, this is a constant in the universe, and that kind of thing. So it's modeling exponential growth. And so in this case, I'm saying that y will grow exponentially with time. Of course, the common example is population growth. Now people are forecasting an exponential collapse in population of human population on Earth for the next 100 or 150 years. But for years it was exponential growth is going to wipe us all out. So exponential growth. So over time, if you start out with a couple rabbits, you wind up getting many rabbits relatively quickly, right? And so that's the idea of this model. There's a little blurb here about Bernoulli and Euler, and where these relationships come from, which you can investigate, but it's pretty cool. Okay, so I just showed you basically how to solve this analytically. Not exactly, but here's the code. So I just showed you these expressions, matplotlib because I want to plot the result, numpy because I want to invoke some math functions that are available to me in numpy. In this case, what I'm going to do is I'm going to set a range of values of x. So if I go back up here and I'm talking about population growth, then x represents time in this particular case, right? I guess I could have written a t there instead, but you get it. And so I'm creating a set of numbers here, and I'm using np or numpy to do that. And this arange function gives me a set of numbers. So let me just actually add a statement here. I'm going to say print x, just so you can see what this looks like, and I'm going to run it, and I get a set of numbers. And you can see it starts at 0 because I told it to start at 0, and it counts at 0.1 intervals until 1 less than that final number. So that gives me the A range. If I wanted to print out to a different range to 10.1, if I really want 10 in there, I could say 10.1, it'll go out to 10 in that case. Often it just doesn't matter too much. But the point is I'm getting this set of numbers, right? And then when I plot, just like I did before with this PLT command, I'm going to get rid of that print statement. When I get this PLT command, I can say, well, I'm going to plot x, time in this case. I'm going to label the x-axis as time. And the number of rabbits is going to be just np.xp of x. And so this is the analytical solution to that expression. So over whatever my time interval is, doesn't really matter in this case, but I get this exponential growth in rabbits. And so this is the analytical expression, super easy to write. Now, Euler was super interested in numerical solutions to analytical equations. Of course, he was working without these tools, so it was a bit hard for him to implement these, but he realized that a lot of ordinary differential equations don't have analytical solutions, right? And so how do we approximate this with a numerical solution? And so one way to do this is with something called Euler's method for approximating the ODE. And this is basically what he did. He said, well, I can forecast the quantity in the future time, the abundance of rabbits at time I plus 1. If I know the value now, and I take a small step, h, that's a small step in time, and I might multiply that by my function. So let's just look at what that means in code because it's easier to understand. Okay, in this case, if I go back up to my analytical expression, the change in rabbits with time is equal to K, can ignore K for the moment, times the number of rabbits currently. Okay, so at I plus 1, the change in the number of rabbits between I and I plus 1, that's dy dx, is going to depend on the current value. Okay, so I write a function, and in this case, I'm just calling the function f. It's kind of boring. Depends on these two arguments, these two values I'm passing to it, x and y. And all I do is return y. And you can see by the indentation here that this is the function, right? Def return y. That's it. So that's implementing this expression up here, right? Dy dx equals ky equals y. Okay, so that's all I'm doing there. And I set my initial conditions. X equals 0, or y, the number of rabbits, I guess, is equal to 1 at time equals 0. Should probably call that 2, but anyway. And then I'm going to step through. Oops, let me just get rid of that. Let me just make sure this runs. Sorry, I was messing around with this before class. Okay, so I'm going to set my step size. I'm going to just arbitrarily say 0.01, and then I'm going to introduce a loop. So while x is less than 10, okay, so I'm going to, up here in my numerical solution, I ran it till time equals 10. I'm going to implement Euler's solution. So k1 is going to be equal f of x. Y at the next step is equal to h times k1, and x is just going to increment by h, right? So h is my, just to reiterate, h is my little step size, my interval here. F of xy is this expression. Could get a lot more complicated in this one. This one's just returning y, and I'm incrementing each time by h. Okay, so if I print this out, this is a numerical solution, right? Because I'm discretizing time into steps. And in a lot of the codes we're going to be using in this class, we're going to discretize time or space into particular steps, and we're going to have approximations to solutions like differential equations. And so this is Euler's approach, right? So if you don't remember how to do the calculus, or seems impossible to do for your particular equation, you can always implement Euler's solution. Now, let's look at the output of this. Okay, so I'm printing out here the Euler method solution, and it tells me 21,168 rabbits after time equals 10 intervals. And the exact solution I got above was 22,247, right? That's just solving this expression, which I can do because this is a simple example. Okay, so there's a difference in the number of rabbits. So, you know, say you're modeling population growth or the decrease in abundance of a radiogenic nuclide in a mineral as a function of time or something like that. And use Euler's approximation, you'll do pretty well, but not get the exact answer, right? It's an approximation. And of course, Euler, who was doing these calculations by hand, was like, that's good enough for me. I'm solving this problem. But as computational tools became available, people came up with other solutions to code an ordinary differential equation. And a famous solution, and probably the most commonly used solution, is to use something called Runge-Kutta, the Runge-Kutta solution. And the idea behind the Runge-Kutta solution is it takes the function I'm using in this Euler approximation and it rewrites it in a more efficient way. And there's sort of different styles of implementation of this. This one's called a second order Runge-Kutta solution. It's second order because I add an intermediate step. Let's just look at how this works here. The expression is the same. Okay, I've I'm using the same function I used up here, define f, x, y, return y. That's it, okay? And so I'm saying x, these are my initial conditions, x equals 0, y equals 1. I'm going to set a step size, same step size I used before. I think that's the same step size I used before. Yeah, 0.01 units, whatever it is, seconds, years, whatever. And then I'm saying that while x is less than 10, that's what I did before, while x is less than 10, go through this loop and do it, okay? And so instead of just saying k1 equals fx and then f of xy, and then using that to calculate the new value of y, I add this intermediate step. So Runch and Cutter are two guys working on this problem of approximation, I guess in the 50s and 60s, 1950s and 60s. They said, well, I can probably get a better solution if I just add this intermediate step in Euler's approach. And so basically they take a half step. And so you can see what happens is I define a variable k1. That's just as I did it before, call f of x, y. And then I say, well, k2 is going to be equal to this same expression, but instead of passing it the value of x and the current value of y, I'm going to pass it x plus a half step and y plus a half step times k1. And then I'm going to find the new value of y, number of rabbits, is going to be equal to h, this cumulative value of h plus times k2, and x is going to be incremented by h. And so I'll come back to that in a second to explain it a little bit more. But what happens is I get a remarkably better answer, right? So now I'm within 4 rabbits of the exact solution just by adding this additional half step. So I've been using the computer to approximate the solution. When I use Euler's formula, I get a pretty good solution, honestly good enough for a lot of volcanology, but I can get a much better solution right away with a very small computational cost if I implement this Runch-Kutta 2 method, right? And so I'm getting a much closer answer to my differential equation. Okay, so if I look at this, let's look more carefully at this loop because it just blew by you a little bit. And we've been on the call a while and it's hard to follow this stuff. So when I say k1 equals f of xy, all right, okay, at f of xy, what the computer understands is f is a function and x and y are the values I'm passing to the function. And I passed x and y up here, right? I passed 0 and 1. And what's f? Well, f I defined in the cell way back up here, right? F is just returning the value of y. Why did I say that? It's because dx dy up here in this expression, just forgetting about k for a minute, just depends on y. That's it. Okay, so that's where I'm at on that. And then as I go in the loop, I say, well, now I'm going to increment x. In this case, x is time, right? I'm just counting through time. And so every time through the loop, I increment time, I increase time by some value. So let's just look at this line here, x plus equals h. Well, when I go through the loop the first time, x is equal to 0. And then I get down to this line and I increment by h. So now it's updated to x equals x, the current value, plus 0.1. So this expression essentially means x equals x plus h. Now, only a computer scientist could come up with this expression, right? Because x equals x plus h, my 3rd grade math teacher will be quite upset with that, right? So that's what that's saying is I'm updating the value of x by h. And usually in code, we just write it with this plus equal h. It's just shorthand for doing that. Okay, so that's incrementing x by h. And y is updating by h times k1. So I could just put fxy down there instead of k1. I'm just making it a little bit easier to read there. So just by that step, I get the approximation, which is pretty reasonable in my code. I'm much better to I'm much closer to an analytical solution. And as always is the case, if I just like increase, or if I decrease my step size, so I'll increment 1/1000th of a unit in time instead of 1/100th. So the difference in this case before was 1,000. If I run that again, now my difference is 100. So I can make the computer work for me. I can get a better answer just by changing my step size, right? And so we do that a lot in code. And you always have a trade-off between, well, how accurate do you think you should be, and ultimately how fast your code's going to run and what your step size might be. But when people talk about step size, when we get on to things like Titan 2D or IMEX lava flow codes, or better models of magma chambers, then this is what we're talking about, how well we're doing that approximation. Okay, and then just very briefly, Runge and Kutta went on, and they said, well, let's just keep going on this. And so they've got the second order approximation, which I already talked about. And then there's a fourth order approximation. You can see what's happening is I'm just increasing the splits in doing this approximation. And when I do this, I'm not going to go through this in detail, but when I do this, suddenly I get a much better answer. Let's see, I should actually keep the step size the same, so I'm not cheating. Okay, but I still get a much better answer, closer to the analytical solution, by using something called a fourth order Runge-Kutta solution. And often when you hear scientists at AGU or EGU saying, I'm solving this ordinary differential equation for flow in a conduit or something, people often land on the fourth order Runge-Kutta solution to approximate that differential equation. All they're talking about sounds really fancy, right? You're like impressed when you listen to that talk. Well, all it is this bit of code to approximate the differential equation, right? Again, then there's a fifth order, and this fifth order expression suddenly gets a lot more complicated, and it has a lot less error in it, but I wind up with, really knowing the number of rabbits in this case. So this is using an algorithm called the cache-carp method, and it's implemented from a method from a book, literally a book called Numerical Recipes in C. There it is. And you no longer need to buy the book. You can get all these algorithms online. But I think this book's been cited like 30,000 times, 40,000 times in the scientific literature, because it contains these algorithms that so many scientists find useful. All right, so this is an implementation of that algorithm, and you can see you get very little error as a result of that. It's sort of absurdly small error. Good to 5/10 millionths of a rabbit in my solution. Okay. So let me go on and just talk about an actual problem. And I saw you all, a bunch of you are doing geochemistry and that sort of thing. And I thought, okay, well, let's look at a geochemistry application of this differential equation, the one we just implemented. Okay, so here's a word problem for you. There's a magma reservoir. The magma reservoir is 1/10 of a cubic kilometer. It's filled with basaltic magma, no bubbles in it apparently, density of 2,800 kilograms per cubic meter. Cool, okay. That's my reservoir in the subsurface. And suppose this reservoir is erupting. It's erupting at 5 cubic meters a second. Mauna Loa 2022, right? Reykjavik Peninsula a couple days ago. Okay, so it's erupting 5 cubic meters a second. And so in turn, your idea is that a primitive magma is getting supplied to the magma reservoir at 5 cubic meters a second. So the reservoir doesn't change with time. So, this would be if you were looking at the volcanic system with INSAR or something like that, and it started erupting 5 cubic meters a second, you might expect the crust to deflate a little bit in response to the eruption of magma, the depressurization of the reservoir. If it's not changing, if there's no change in the INSAR during the eruption, then you got to be compensating for that volume somehow. So we're just gonna set up this problem that 5 cubic meters of primitive basalt's coming in. Okay, so let's say the primitive basalt is a pickrite. It means it's got a lot of olivine in it. It's got a lot of magnesium in it. Let's say 16 weight percent. So we're in Hawaii or something. And the original magma reservoir had a composition of 8 weight percent magnesium, right? Makes sense. Like it's slightly more evolved from sitting in the reservoir and fractionation of olivine or whatever. So what's the concentration of magnesium erupting from the lavas after half a year, right? So in other words, when the eruption starts, we've got 5 cubic meters a second of magma with 8 weight percent magnesium, but that magnesium is getting, that magma erupted from the reservoir is getting replaced by magma at 16 weight percent. And so I've got to have a geochemical change in the magnesium concentration in the magma erupted over time. So, can you model this? Yes, that's the equations we just developed. Okay, so let's check it out. It's called the tank problem. So if you've had a class in differential equations, you've encountered the tank problem before. It's super common in fluid dynamics of all sorts. Maybe it's the change of concentration of your coffee as you drip it through your drip maker or whatever. We'll just stick with magma. Okay, so let's say that XT is the mass of magnesium in the magma reservoir. And so there's a change in the mass of magnesium over time, right? So that the change in that mass of magnesium over time is dx dt, right? It's the change in the mass as a function of time. That's the left-hand side of our equation. That's equal to the rate magnesium enters the reservoir minus the rate at which magnesium erupts from the reservoir. Okay, so the rate at which magnesium enters the reservoir, pretty simple. That's 5 cubic meters per second. That's a given in this problem. And the density of the magma times its concentration. So basically we're saying that 2240 kilograms per second magnesium enters the reservoir. The reservoir is not changing volume with time. So what's going out with time? Well, that's what's erupted out with time is the concentration in the magma chamber, right? Well-mixed concentration in the magma chamber. So the volume of the magma chamber, the kilograms of the magma chamber is 28 times 10 to the 11th kilograms. You can just figure that out. So the outflow of magnesium is going to be the density times the mass flux, which is going to be equal to 14,000 kilograms per second, times x divided by the fraction represented by the reservoir, right? So we've got the whole volume of the reservoir. We've got the fraction of the reservoir erupting in a given period of time, and then the concentration of magnesium in the reservoir. And so this sets up the initial condition. So initially, we said at time equals 0, the concentration of magnesium in the reservoir is 8% times the volume of the reservoir. So I've got 2 times 10 to the 10th kilograms of magnesium in the reservoir. And then so my differential equation is dx dt is equal to that 2240 kilograms per second, right? Minus 14,000, the kilograms per second times the density of the magma times xt divided by the total number of kilograms in the reservoir, right? So that's the differential equation for this problem. I guess I'm going pretty fast here, so I guess you can go back and check out exactly where these numbers come from, but it's, I think, explained pretty well up there in terms of the change in time. The change in time is equal to the concentration that enters the reservoir minus the concentration that leaves the reservoir, right? Makes sense. Okay, so you might go, that's a showstopper. I'm not really sure how to solve that problem. So let's turn to the computer and do it. We'll do some overkill. We'll use one of these fourth order or fifth order Runge-Kutta solutions. Okay, so how do I solve this? Well, I'd have to define f, which is a function of time and concentration, right? That's my function. And that's just equal to this expression, right? So notice how that parallels my markdown. And so it's easy for me to write the ODE as a function if I've written it in my markdown up here, which is what I did. Okay, so that's the function. And then here I've cast the Runge-Kutta solution as a function also. And so I just implement it down here. That returns y at a new condition. Okay, so let's say I've got these initial conditions. I say t equals 0 at the start, and I've got x equals 2.24 times 10 to the 10th. That's the concentration of magnesium in the reservoir at 0 seconds. That's 0.8 times the volume of the reservoir. Cool. Then I've got my initial time step. I don't know what it is. I'm just going to implement it with h equals 10,000 seconds. This it's a small eruption rate and so on. And so I'm going to run it for half a year. That's 0.5 times 365 days, 24 hours, and so many seconds. So x total is in seconds, right? And it's run for half a year. So then I just solve it. I call my function, I pass it the variables, and I print out the answer. And when I do that, I get, after half a year of eruption, I've got 12% magnesium erupting from the reservoir. So all I've done is I've set up my differential equation as a tank problem. You can think of a lot of chemical variation that you would expect to see here, and you can model in this way if you're, if that floats your boat. I set up my ODE. This is just the same function I called before. This is the same function up here that we just worked through a minute ago. I specify my initial conditions, I solve the problem, and I get the concentration after half a year of eruption. So basically what's happening is, as the lava erupts and primitive lava comes in, I expect the concentration to change with time. And that's a real observation in Hawaiian basalts, right? So we can see that kind of thing going on. Okay, I can modify this a little bit. I'm just going to modify it by adding a line down here which creates a set x out and y out, and those are the values of time and concentration as a function of time. So here, after I increment these values inside this expression, I just keep track of the current values. And so we often want to do that when we're solving ODEs to see how things are changing with time. And so now when I call it, I print out my result, translate it into years. I normalize output to years, and I normalize the output to concentration. So using the tools I used before, this is the change in concentration in the lava flow as a function of time, given these conditions, right? Given that magma comes in and magma goes out, different concentrations, solving that ODE. So I know that was a lot to go through, but we've just got this limited time, And the idea is to go back and explore these expressions and see if you can get some use out of it. So down here, I've talked about an additional application. So, if you study flow, geophysical flows at the surface, an issue is that pyroclasts change in size as a function of distance they're transported, right? And so you should be able to find like how the particles are breaking up in a pyroclastic flow as a function of how far they've been transported given some initial condition. So in other words, if I have a pumice that's the size of a football, soccer ball, and it's erupted from the vent and it travels kilometers downrange, what should the median size be as I go with distance? So that's exactly the same problem. And so this particular problem explains how to solve that. Again, it's just like the tank problem I just showed you. And of course, there's all kinds of assumptions in the use of this equation, which you need to think about. And the minus sign here means the particle size is decreasing as a function of time, right? At some rate variable a, which is like k in the previous expressions. And you can even implement it for a mean particle size or a mean and standard deviation particle size. So you can implement this expression just following the example of this notebook, right? And that's the idea behind the notebook, is you can take it and develop some, additional ways to go, right? Additional problems to solve. Okay, that's a lot. I'm just gonna show you two more notebooks which you can look at pretty much on your own time. I'm gonna look at this. Here's a notebook also on there. This is the second one. It's called Pressure in a Magma Reservoir and Expected Deformation. So this is slightly different. It's combining the two ideas I've expressed in this lecture so far, that of the pressure or volume, if you want, of the magma reservoir, and this problem of flow in the reservoir. So I can't remember who developed this, who first applied this in volcanology. It might have been Claude Chapard, probably somebody before him, actually. So the change in pressure in a reservoir as a function of time is going to be equal to a variable called mu, which in this case is not viscosity. It's the shear modulus. Should probably use a different variable there. Sorry, I didn't. And then divided by the volume of the reservoir and the magma flow into the reservoir and magma flow out of the reservoir as a function of time, right? So if you wanted to look at how the pressurization of a magma reservoir is going to change as a function of time, you can relate it to these physical parameters. Okay, so I can solve the same thing. I can solve this equation the same way. And honestly, this, obviously has an analytical solution, but it can be super lazy and just implement my Runge-Kutta formula again and do the same thing. So let's look at this. Okay, so here's my fourth order Runge-Kutta expression. I'm passing it the variables in a slightly different way here. I'll come back and explain that in a second. Let's just look at the output. I implement my function. I called it f before. Now I'm just calling it the derivative. I don't know, whatever you want to do. And I'm passing it these variables, right? It needs to know time and pressure. It needs to know the shear modulus, that's mu, the volume of the reservoir, the flux in and the flux out. And if I know those things, I can return that expression, right? That's my function, right? That's the function I implemented up here. No big deal. Okay. Now I'm actually passing it several other values. And so I can specify something called a keyword argument, quargs, keyword argument. And this is how I specify a keyword argument in Python. It's one way to do it. I've got my shear modulus. So you can look at this syntax in quotes with a colon, and then the value I'm just using for the shear modulus. the volume of my magma reservoir, the flux in and the flux out. So that all those arguments are sort of bundled together, and I'm going to pass them to my Runge-Kutta solver as quarks here, right? And the asterisks just mean I don't need to know how many variables are in my argument. Just copy it for the moment. And then I specify my initial conditions, and I solve for a step size, an initial step size, and a change in time. And I solve the ODE. And so I just plot it up exactly as I did it before, and I get the change in pressure as a function of time. Lo and behold, it's linear. That's what I would expect, right? Because of that's my relationship. So it's a trivial solution in this case, but you can see how I implemented it with this quarks approach. Now I just want to get one step fancier for you. And I'm going to say, well, okay, this is the same expression, but I kind of fooled you, right? Because the flux out probably depends on the pressurization of the magma chamber, right? So now I'm getting a little bit more interesting with my ODE, because Q out actually depends on the magma pressure in the reservoir. So this is where things get kind of complicated, and you're like, oh, this is hard to solve. But we have expressions for this that we already talked about. So Q out, if I assume it's laminar flow in a conduit, then I have an expression for that. That's the expression that I started with today. And I got dP dx, and I can approximate that as, you know, the overpressure as a function of distance along the conduit. And so I've got this expression for Q out. And so somehow I'd want to substitute that in here to solve for the change in pressure. But now I've got this differential problem, right? Where I've got a change in the pressure as a function of time depends on the current pressure in the conduit. That sounds an awful lot like a rabbit problem, right? The number of rabbits in the next time step depends on the number of rabbits now. It's the same issue. So I'm going to implement a solution in exactly the same way. Forget this part for the moment. I'm going to say, okay, I'm going to solve it with my fourth order Runge-Kutta code, which I've already gone over. Now, here's what my function looks like. I'm trying to blow that up for you. I bet you guys can't see it too well. There it goes. Okay. So, well, here's my function. It depends on all these variables. This is just the solution to my function, exactly the way it was before. But when I call that solution, I want to first solve for the Q out, right? The flux out. So that for that, I'm actually going to call a second function. So here it says volume flux out is equal to flux out and all these variables. Here's the expression for flux out. That's my laminar flow expression that we implemented earlier today. And I'm going to return Q. So what's happening is my differential equation, which is here called deriv 2, depends on another solution, which is the flux out, and that's this analytical solution, which I can pass to it. That's the analytical solution we implemented earlier today. And so pressure is on the right-hand side and on the left-hand side of the equation. Okay, so now I'm going to call it just as I did before. I'm going to specify initial conditions. I'm going to solve it, and I get the pressure as a function of time, or I can, oops, there's a little bit of issue there. That's okay. I'm going to solve it as a function of time. And here's how the pressure changes in the reservoir as a function of time if the output flow depends on the pressure in the conduit. And you can see this has exactly the same form as the rabbit problem, right? It's this exponential curve. It's asymptotically approaching some pressure as a function of time, right? So, wow, that's pretty cool. And then, of course, you can take that pressure and you can calculate, say, the deformation you would expect to see at the surface of the Earth as a function of that pressure. And so I can say, well, what's the maximum deformation I expect to see for that change in magma pressure if I've got rheological properties of the crust, and I make some assumptions about the geometry of the magma chamber. And so I can take that differential expression and say what the maximum displacement is going to be as a function of time for these initial conditions where the flux out depends on the pressure that's inside the magma chamber, right? And so this is getting to be like a solution to a real problem where if someone is monitoring the pressure in the reservoir as a function of time, sort of the displacement of the Earth's surface as a function of time, using INSAR or using, you know, continuous recording GPSs or something like that. And, you know, the MOGI solution, that analytical solution for deformation, tells you what that means in terms of pressure. Great. But what does that mean in terms of magma flux in and out of the reservoir through the differential equation? I have to relate it back to this, right? And so people like Kyle Anderson and Paul Siegel have implemented these kinds of solutions relating deformation signal to conditions in the reservoir. And, you know, if you're then a geochemist, you can say, well, I really care about what this means in terms of the concentration of magnesium I'm going to see in the lavas. You can include that and so on. So it opens up a universe of problem solving. And the point is and I know it's a lot, but you can go through these notebooks, study that, and see where we're at. You know, just see sort of basically what that approach is. And what I want to tell you is it's not as complicated as it might seem at first. And if you familiarize yourself with the notebook, you might be able to solve a bunch of problems. So there's one more notebook. I'm not going to go through it. This is an ODE for ballistic transport. You know, there's a lot of papers out there about how blocks fly through the air during phreatic eruptions or phreatomagmatic eruptions or whatever. And the solution for that is exactly the same. It's a set of differential equations. You implemented the solution to those differential equations using Runge-Kutta, and these are the same codes I used before, and you can calculate the ballistic trajectory. So it's an extremely useful tool for us in science. And anyway, I hope that introduction helps. I know it's a lot. It's an introduction to notebooks. Maybe it's an introduction to ODEs, but I'm trying to whet your appetite about this being a really cool thing to do, to learn more about how the Earth works and how to model it and that kind of thing. And I'm tired of talking. Sorry, you're probably tired of listening. I blasted through that. What about questions on that stuff?
I had a question for you, Chuck. So, for example, for the last example of the magnesium concentration, if you use a second order Runge-Kutta, how much different the result is? Because you got like this time you got a fraction between 0 and 1, and so it's a percentage. So it's kind of different than the rabbits where you have like very large numbers. So so I guess like how much difference do you get? Like what in which decimal do you have to like move in order to see a real difference?
Well, right, and you know, often in papers you see, oh, we implemented a Runge-Kutta fourth order solution, blah blah blah, and you're like, ooh, that's impressive. But yeah, you could just do it with a 2 just as easily, and probably get exactly the resolution you need. What happens is it kind of depends on how complicated the equation becomes. So if you're using a conduit flow model, and you know, I showed you an equation where you had like one constitutive equation, right? The the flux depends on the pressure, which is also on the left-hand side of the equation. So that's one level of complication, but you get into the like Confort or Conflow models where, maybe you're also trying to calculate the bubble density and, recalculate the density, and maybe you've got variation in the radius of the conduit as a function of depth. Suddenly it becomes kind of sensitive to that, and you really do need that fourth order solution. So it depends. For the examples I gave you today, second order is fine for everything. You don't really need that more complicated solution. The fourth order is overkill in that case, but I just want you to be aware of it, because sometimes you get into problems using the second order if there are a lot of interrelationships. And that's why they go to fourth order, and like Andy Woods and Larry Maston and Giovanni Macedonio, they all go to fourth order when they're dealing with conduit flow or something like that, and they want to account for 8 different processes happening simultaneously or something. It can become a bit messy.
Yeah, so we're going to talk about that next week. We're going to talk about conduit flow. So I guess we're going to introduce, Conflow probably, and show an example on Victor, and then show you how when we add more complication to the equation, like how much that matters for sure. Is there any question? We have a little bit of time for one more question, 1 or 2 more questions. Or we can leave it for next week, because I
killed everybody. They're like,
no,
leave.
we can leave that for next week, so then you guys have 1 week to look again at these notebooks. Just a clarification: they are in the folder called 2023, right? Victor short code, but it's a 2023 one, the one from last year,
probably,
right?
yeah. I didn't change them from last year.
Just to make sure everybody can find them. I think they are. Let me just check. So they're in the shared folder.
I didn't know there were different years, honestly. Sorry about that.
Victor short courses. Oh, it's just Victor short courses. It's in the shared folder, and it's called Victor short courses. And then you have them all here. So it doesn't. There's no year. So it's good. Okay.
So
and it's part 7. Part 7 ODE.
Right. And if you are willing as a participant in the class to go back to that tank problem and see if you can implement it, and see if you can vary it for something that you're interested in. So I gave you an example of particle size in a Lahar PDC. You could implement that solution, or you could implement simply another sort of concentration problem in a tank problem. That would be fine. Or
you can do everything. Like in geomorphology, we're using the tank problem for like almost everything, like from heat conservation to solar radiation, like on Earth, or hill slopes, diffusions. It's amazing. It's amazing how much thing you can solve with a tank problem.
Yeah. So if somebody's willing to, I encourage you to like if you just listen to me for an hour and a half and you're like, well, that's terrible, and I'm not gonna deal with that anymore. It's okay. We're gonna take a bunch of different approaches in this class, but you'll get the most out of it if you try to implement these 1 or 2 of these solutions in your own notebook.
Yeah, so I guess it can be the assignment for next week. You guys can look at that and find out if you can implement it for your own problem, and then maybe somebody can show us that at the beginning of the class. And very quickly, Sam, I don't know if you're still here, but there was one participant that said that didn't receive the email confirmation for getting a Victor account. So if you could look at that and make sure we can send these confirmation emails to everybody, that would be great.
Sure. Yeah. Who was it?
I think it was Mickey.
Hi.
Oh
yeah,
yeah,
it was me, but yeah, I got that email, so I'm all good.
I did that just now. That was my
Okay.
bad.
Perfect. All right, cool.
Yeah, so be sure to sign into Victor and check things out, even if you know, you're just looking around. Oops.
All right, so I'm gonna stop the recording and thank